In the last video, we saw the determinant for a 1 by 1 matrix, which was trivial, a 2 by 2 matrix, and the 3 by 3 matrix. And we saw that it corresponded to volumes or areas of parallelograms or parallelogram type objects. Well, we want to extend the definition to any matrix, so a matrix of any size. And in order to do that, we need some preliminary definitions. So the first thing we're going to define is for a matrix A, with entries lowercase a, I, j for I and j equals 1 up to n, say. We let A sub ij denote the matrix obtained by deleting the ith row and jth column of A. So for example, if we have this matrix A is equal to, so let's do a 3 by 3 example. A22, A23, A31, A32, A33. Well, let's take say A13. So that means I remove the first row, or the first row. So that's the first row, and the third column. First row, third column. So this gets removed, and now this is a 2 by 2 matrix, and it's going to have A21, A22, A31, and A32 as its entries. That's the idea. And we're going to say we let Mij equal to the determinant of Aij be called the ijth minor of A, and Cij equal to -1 to the I plus j Mij be called the ijth cofactor. So now we're going to actually be able to define the matrix or the determinant of a matrix in terms of these quantities. And the definition we're going to use is generally called the Laplace expansion of the determinant. So definition: the determinant of a general matrix A, we set that equal to, and this is an expansion along the first row, C11 plus A12 C12 plus all the way up to A1n C1n. But this is also equal to, right, by definition, A11 M11 minus A12 M12, because remember that Cij has this -1 to the I plus j factor here, and 1 plus 2 is 3, so that's odd, and we'll have -1 to an odd number is negative, plus all the way up to -1 to the n plus 1, A1n, M1n. But the thing is, so this we could take as the definition, but you can actually expand along any row or any column. So this is also equal to so let's suppose we expand along any row, right? So this is expansion along the first row. AI1 CI1 plus AI2 CI2 plus, that should be a 2, plus AIN CIN. But this is also equal to expansion along any column, right? So I have A1J C1J plus A2J C2J plus all the way up to A NJ CNJ. So what we obtained here is that we define the determinant recursively in terms of determinants of submatrices of a matrix. And that's actually why we first have the word matrix, right? So we first had a matrix or organized things in terms of a matrix uh, so that we could actually study determinants in the matrix, and this was done by Sylvester. And that's why we call it matrix. Matrix is Latin for womb, right? And at the time, it was thought that this is the object from which all determinants could be born, right? Determinants were the most interesting object at the time because they helped us understand solutions to systems of linear equations, which have been very important. So we've talked about determinants in terms of solutions to systems of linear equations, but there's also a really nice way to think about things, right? So because of the distributive property, whenever we have two columns, say x1 and x2, so let x1 and x2 are column matrices. So we're kind of into a new thought here. Are column matrices. A is an n by n matrix, and suppose S and T are real numbers. We have that A times Sx1 plus Tx2, right? Because of the distributive property and because I can commute out scalars, right? This is going to be S times Ax1 plus T times Ax2. And whenever you see something like this, when you can get A into here, that means that A acts like a linear transformation, right? So why do I say linear? It's linear because if it can do this, it takes lines, right? So this ends up being a line, right? If I let T vary wherever it could possibly go, then I would get a line here, and we'll talk more about lines later. But basically, this line is going to be mapped to a new line over here, right, where T is allowed to do whatever it wants. And maybe S was fixed. If S and T are both allowed to vary, then this is actually saying that a plane will get mapped to a plane, possibly degenerate plane, right? We'll talk more about that later. But as a linear transformation, this has a new interpretation, right? So we can interpret the determinant in the following way. We can ask, for example, in the 2 by 2 scenario, we can ask the following question. Say this is a 1, and this is 1, and this is 0. So we have the unit square here. So this is the point 1, 1. And we ask, well, if I transformed all these points, right? If I took this 1, 1 as a column vector, so I could say have this column vector 1, 1, and I have this column vector 0, 1, this column vector 0, 0, and this column vector 1, 0. Well, what if I hit each of these guys with A? Well, what am I going to get? Well, this guy is going to be the first column, so this guy gets turned into the first column of A. So this will be A, 1, 1, A, 2, 1. This guy is going to give me the second column of A. So this is A 1 2, A 2 2. And this guy is going to go to A 1 1 plus A 1 2, A 2 1 plus A 2 2. Right? So the unit square, which is of area 1, gets mapped to this parallelogram, which is of area equal to the determinant of my matrix. Right? So this tells us that linear transformations, the determinant of a linear transformation, is telling you how volumes are distorted, right? So this changes the unit volume into volume that's a multiple of the determinant, possibly with a negative sign. So that's kind of a weird thing. We can't really talk about negative volumes, of course. Um, so if we take the absolute value, then it's really how the area is distorted, and the negative comes from an orientation parameter, right? So that's kind of interesting. And so you have the following basic important property, and this was first demonstrated by Cauchy, right? But if you have two linear transformations, right, and you combine them, right? Suppose these are two square matrices, A and B. Well, if I distort this volume by the volume of A, right? So I send this through an A mapping, and the unit volume gets changed here, right? And then I send it through another B, well, I get distorted by another volume, right? And in the long run, when I combine these two mappings, what's the net distortion of volume, right? Well, that turns out to be the distortion of the volume caused by A times the distortion caused by B. And this is a very important theorem. This is a very important idea. This gives us a nice algebraic structure for the determinant. This is beautiful. So, and this holds for A and B, both n by n matrices. Next time, we'll actually talk about certain important determinants that we can actually compute.